Everybody ready to roll?
Yeah, about ready.
How you doing, man?
Well, what do you know, man?
Still taking pictures?
Of course. Of course.
Getting paid to take pictures.
They take pictures. You can't hardly do that.
Life.
Tell me. Hanging out on your boat, looking at, you don't have to have any toxic chemicals anymore or nothing. It's all digital. It really works
About
out.
everything, huh? Did you buy your boat? You got a boat?
Yeah. I had a boat last time I knew.
Yeah, I don't remember that. I didn't know you had that.
Yeah, the camera. What's been the latest? So we've upgraded.
What are you doing here? You should be out on the water.
Yeah, I was there last week. Now you gotta spend some time on that.
Yes.
Little as possible. As little as possible. All right, so where are we at for time here?
On the button. It's not far from now.
Best practice. Come on, sit down, man. This is the best place. The only place to be. It's right here. How bad can it be?
Depends on how much they have for lunch.
That's it. I don't know if you believe anything this way. You have to sign that, sit down. Where I'm supposed to be. Uh-oh, it went that. Wondering where he is. All right, well, no further ado, I'm Sean Dolan, this is Best Management Practices 2. We're not mired down with those people with one, we got 2 going on over here. Second generation of best practices, so we got to get their introduction next door, and then they come over here when they want some advancement, you know, and they really want to get to know some really cool stuff, like Dave's going to tell us all about here. So Dave's from Spectrum and Analytics. Spectrum Analytics, he's been there for 6 years. No, 6 years, he was working in the Air Force is what he was. He was an electrical engineer. When he started this analytical experience, total detection limits, and companies with too many syllables in them to pronounce, and now he's the distributor and the owner and the main guy. Respect.
We're not the same spectrum.
Oh, we're not different spectrum.
It's a unique spectrum.
Oh, well, there we go. All the better. So with no further ado, Air Optics is the name of the game. Tell us what you got to tell.
Appreciate it. Thank you. Again, David Nicholson, appreciate everybody for coming today. Basically wanted to give everyone an idea of some of the technological advancements that we've had with near infrared and mid infrared and in situ extractive and also open path analyzers. We'll kind of go over a basic overview of Air Optics. I think it's important to understand who Air Optics is as a company and the contributions that we've had to R&D globally around the world that's made some of these measurements that we've had today to meet EPA and emission guidelines possible. We'll also give a brief overview of the absorption spectroscopy, some of the past developments, identify some of the significant improvements, a couple of examples of these applications so that you can see the detection limits that we're achieving today, and also explain where Air Optics is as far as their capability and process analytics. So first, to give you a little background about Air Optics. Air Optics is a manufacturing facility, small medium enterprise company that's based in Poland, which was founded in 2010. Manufactures obviously gas analytical equipment with an ISO 9000 certificate. They also have in-house R&D department. Main applications are process control, power industry, pretty much all of the industries as a whole. I mean, with where we're at right now with near infrared and mid infrared, it's kind of difficult not to find an application that's gas that we can't do. And there also has currently a global distribution and service network set up around the world. So it's pretty important for us to understand a little bit about the history. I don't like to harp on it too much, but it's to kind of give you an understanding where everything is coming from. So Dr. Powell Klaczynski initially was working for a company by the name of Alt Optronics. This company was the first company that came out with a ammonia in situ analyzer. He was also responsible for redesigning the algorithms and the optical bench for that analyzer. And that was previous to Siemens acquiring that company in 1999. At that time, he was the chief physicist for about 10 years, and he was responsible for the LDS-6, which everyone is aware of now. Going a little bit further than that, the Cytrans SL came out, which was their O2, SIL2 analyzer. And then in 2010, he created his own company, which was Air Optics. Now you'll see there's a little bit of a gap there between 2010 and 2012. And the reason that is when he first created this company, he worked as a consultant. So he worked for a consultant as companies that we know today with Emerson for their moisture applications, Miller Toledo, and a few others, okay? In 2015, we basically came out with the gas eye cross duct. Significance of this analyzer is that we started getting into the mid-infrared for ICL lasers on single path analyzers. And then the multipass came out. That multipass allows us to do multiple lasers into one. So we can do up to 6 lasers in one analyzer. So now it gives us a lot of flexibility to meet those customer needs. And then, of course, in 19, we've got the extractive analyzer, Harriet cell, which a lot of us are familiar with. And that gives us significantly lower detection limits if we needed to achieve something much more accurate. The 4 icons that you see at the bottom, this is the European projects that Dr. Klaczynski actually sat on. These were European projects where scientists from all over the world come together to help develop more and improved lasers and chips. So we've got the infrared, we've got the mid-infrared, and then we've also got some QCL technologies that were created during this research project. What's even more significant is the wide laser project in which he sat on, and worked directly with the chip manufacturer and came out with the first formaldehyde. So a lot of us have heard the papers today and explanations around the open paths, the formaldehyde. This was one of the applications that he was directly responsible for. So we use the acronym laser a lot. We really don't, you'd be surprised how many people don't know what the acronym stands for, right? So it kind of speaks for itself. Light amplification by stimulated emission of radiation. So our technology is working obviously off of the Beer-Lambert's law, absorption spectroscopy, where we're looking at the amount of electromagnetic radiation going through an open area. That open area will excite that molecule. That molecule will absorb some of that energy. And then we're looking at the loss on the B side or on the very end. That loss of energy is proportional to the concentration between point A and point B. So here we see our laser beam that's entering into the process. Seeing the molecules or our gas in the middle. And then we also are measuring the amount of loss on the end. So every molecule has a certain amount of energy or atomic weight. And that atomic weight is based on the number of protons and neutrons and electrons that we have. So what we're looking at is those vibrational bands that are absorbing in the near infrared and mid infrared region. So as that electromagnetic radiation passes through the gas, you'll actually have some absorbance of that electromagnetic radiation, and you'll see the actual electron move from one shell to the next shell. So it is absorbing at that point, right? When it comes back down, it's moving to another transition. So that loss in that radiation from point A to point B is what gives us the concentration in our analysis. So again, with the amount of lasers that we have today, they're very, very accurate. Peltier coolers allow us to keep a temperature control on the lasers as well. So we're able to tune those laser wavelengths to a magnitude of plus or minus 100 nanometers or less on a single wavelength. So we are scanning across the actual wavelength of this at multiple times of a second, up to 10 kHz or more. And then we're looking at the baseline, and again, that ratio of the baseline to the absorbance of the light is proportional to the concentration. This is a picture of their R&D, just to kind of give you an idea of what it looks like back at the factory. A lot of scientists, a lot of R&D goes on to keep us up with being able to give a very high accurate measurement, and helps with the development of what we need to come into the future. So why is that significant? So if we look at this chart here, we all know that in the past, we've been pretty commonly in the near infrared region, and those were the spectrums that we had available at the time. But now with the advancements with ICL and QCL, it gives us a pretty wide range of spectrum, a new spectrum that we can pick from to go into new applications. So if you see here, we're looking at anywhere between somewhere around 3,000 to 6,500. And we can see all of the different wavelengths that we're able to do within the mid-infrared. SO2, for instance, was something that we never could do in the near infrared. If we look at this next chart, we can see that in acetylene, in the near infrared, we had a very, very low absorbance. But now when we jump into the mid-infrared, now we're talking about 30 times stronger worth of absorption spectra that we can pick from. So that gives us a better detection limit, better spectra, better absorption. Same thing with NO and also with CO. So you can see that line, the second line is our NO and also and our CO line. So we're basically just showing you what it looked like in the near infrared and now what we have available in the mid infrared. So some of the advancements. So this is our gas eye. It's our cross duct analyzer. This is the analyzer that we now have the ability to do near infrared and mid infrared within the same analyzer. A lot of different gases here that we can pick from. But for this analyzer, we have the capability of being able to incorporate up to 6 different lasers into one optical bench. So there's been a lot of advancements in our optomechanical bench. So it allows us to be able to make a lot of different measurements with a very low detection limit and also with a very, very low etalon noise issues. And of course, this is our multi-gas. So this is the analyzer that we're using to incorporate a lot of different mid-infrared and near-infrared lasers. There's basically 3 different categories that we really have. We've got the in situ analyzer, we have the extractive analyzer, and then we also have the open path analyzers. It's pretty common across the board. And then these are our in situ flanges. What's unique about this is we have no soft goods in between the actual flanges and the nozzles. So there's nothing to worry about with leaking. What we find that's very important is for the optics and pressure and the safety of the end users. A lot of times we'll see optics where they're limited on the amount of pressure that they can handle, maybe up to 5, 10, or maybe even 20 PSI. The issue is when you start getting into high pressure in situ applications, you have a safety issue with the actual optics. You may have polymers that build up on the nozzle. You may need to steam inject. There's a lot of different applications where you could put the optics at risk. With ours, we actually have the ability to supply up to 580 pounds of pressure against those optics. So really no need for a full ported ball valve to be able to isolate the actual flange. The other unique thing is it's also a quick coupling. So if you ever needed to take the analyzer off and do maintenance or do a calibration, whatever the issue may be, it actually has a quick coupling. So you're not actually taking the flange off from the process to take the analyzer off. It basically has a nozzle at the very end, slip it in, has an O-ring on it. It's a one-handed deal, so one person can install and remove the analyzer. So if we get down to the open path, like we said, we've heard some of the papers. This was our air optics analyzer that we had in California with the ability to do formaldehyde down to less than 1 parts per billion for detection. And we also had the in situ formaldehyde as well. So if you remember, we talked about the MIR program from Europe. This program was where we actually invented the formaldehyde laser as well and used it in this application. So down to 4 ppm on this application with a detection limit less than 5 ppb. Ammonia and moisture detection, pretty common for SCRs, power plants, and then also for a waste incinerator. So in this application, the customer had 2 in situ TDL analyzers. We had one for the ammonia and also one for the HCl. The NO, the moisture, and also the SO2 was an extractive analyzer, which he pulled out, but had a lot of issues with the probes plugging up. So what we did is we removed one of the analyzers and we incorporated all of the gases into one. So now what we have is a HCl, NO, SO2, and moisture analyzer all in one path length, one nozzle configuration with the ammonia as the secondary. If we look at some of those detection limits for the SO2, we had 5 ppb, or ppm, I'm sorry. We had 0.8 and 0.1 relative to SO2, HCl, and NO. So again, we've got that whole mid-infrared region that we can pick spectra from to give us those analysis where we couldn't get before with near infrared. ppm meter, yes. Yeah, so your ppm meter will obviously change based on the path length that you'll have, right? This is in situ NOx, where we were measuring NO, NO2, and moisture. We all know in our past, previous to mid-infrared, NO and NO2 was very difficult in the near infrared, just didn't have the right spectrum to pick from. So a lot of times you would use a converter to get your NOx, or if the customer was okay with it, you would give them a differential to achieve the NOx as well. So in this one, I think, let's see here, we were 0.1 ppm per meter and 1 ppm per meter for NO and NO2. And then DNOx. So now we're looking at NOx, ammonia, and moisture all in one application. Or we can look at the NO, NO2, and the moisture, and also the ammonia and the moisture, which is pretty common in near infrared as well. But I think the significant thing is if we look at these applications that I'm showing you in some kind of way, shape, form, or fashion, we have some mid-infrared incorporated into the laser. And you can see that the detection lines are pretty significant for us for measurement, and the detection limits are incredible as well. And here's your DSOX. So again, you're looking at SO2, HCl, and moisture. The SO2, HCl, moisture, and CO. There's just a numerous amount of combinations that we can go with. And our next one, combustion. O2, CO, methane, moisture, and your temperature line as well. So if you're trying to figure out where your stoichiometric formula is, how much O2, excess O2 you have, where your methane is at, and where your CO, you can get that all in one measurement. So with the air optics analyzer, we have no moving parts. We're actually shooting the beam across the actual furnace in the convection section, measuring it on the B side as well. With us being able to shoot all the way across the furnace, we don't have any saturation issues. So sometimes if you get to a point to where your path length is so long and you're using a 2-pass system or a reflector on the other side, you're double the path length. The problem with that is you can actually hit a limitation with saturation on there, and you can't achieve the actual ranges that you're looking for. So we just go one single path across the entire furnace. And then our sub ppm. So this is one of our extractive units that's here in the rack. This was here for the H2S. Obviously, it got us down to 0.2 ppm. And our extractive analyzer will basically have a Harriet cell inside, where the laser beam comes inside between 2 reflective end whether it's highly polished metal or some gold-plated mirrors of some sort. And every time it bounces back and forth between the mirror, we increase that distance or that path length, and that absorbance will actually get us down to a lower detection limit also. And then here we're looking at CO, HCl, moisture, and SO2. And in situ hydrogen purity. So one of the things that we didn't put up here, we were discussing whether or not, but it was actually okay to go ahead. But with the improvements of what we're looking at as far as hydrogen for combustion and as a fuel, we also have the ability to do an O2 and hydrogen measurement in the same analyzer as well. So whether or not you're looking at that rich state or lean fuel state, then you're able to measure the O2 and the hydrogen all in one. So 24/7 continuous operation, no issues with the analyzer. You can see here in the hydrogen purity applications that we can combine between the different species. And get down to what we've got here, 100 ppm per meter and 1% by volume per meter on hydrogen. And on our extractive. So this is where we're actually pulling the sample, going through a Harriet cell, and achieving a detection limit for there. So we've got combinations of O2 and hydrogen, moisture and H2S, a lot of desulfurization units. We're pulling the sample out for H2S, and CO, CO2, methane, and formaldehyde all the way up to ammonia. And you see here for our trace moisture and hydrogen, or H2S, we're able to get down to 0.05 ppm for the moisture and 0.2 ppm for H2S. And currently that's the lowest detection limit that anyone can achieve in H2S today that we know of. So what are some of the advantages? Obviously the mid-infrared gives us an entire different range of spectra to pick from that we never had before. It's pretty reliable. It's low power consumption as well. It's very flexible for us to use the near infrared and mid infrareds lasers all in the same platform. You can do the cross stack measurements. We've got some of the lowest detection limits that you can achieve. 1 second response time, no interferences with the gases. Obviously, we're looking at the mold composition for any specific process. We're going to run that across a high trans, figure out what spectras don't have interferences in their backgrounds, and that's how we achieve the wave number or wavelengths that we want to measure. Highly sensitive, we can get all the way down to ppb, and in some gases we can get down to ppt. Very specific to that spectrum because we're actually tuning the laser to continuous wave for absorption based on the spectrum that we're looking for. Process temperatures all the way up to 1500 degrees Celsius. No moving parts, low cost of ownership. And I think it's even more of a low cost of ownership today with us being able to combine the near infrared and mid infrared together. Because now the customer themselves can actually customize that laser to the application that they have. And proven in use with over millions of operating hours with safety failure fraction numbers that meet SIL 2 requirements. Pretty much some of the same conclusions. So now we have the ability to do that near infrared and mid infrared. Very high speed, low cost ownership, high performance. Again, until now, we were only able to do near infrared for in situ. But now we're looking at mid infrared and near infrared and in situ. And a lot of different gases that we have to pick from, including SO2 and ability to measure NOx with the safety failure fractions equivalent to SIL 2. And that's it.